you should get back, the homework problems back today. And by Friday, I hope you will get back midterm exam results. So if you feel something is not right for grading, don't hesitate to talk to you. Then if it's not working, then it's me. So it should, everything should be fair in this class. And this is a summons which is closed. And this is the one. This will not be a summons. This one will be one. Okay. And this is going to be the primary element. Okay, last Monday, I gave you the full idea and concept of fluid structure in a vacuum problem using the Taylor plate theory, which is developed by G.I. Taylor. It should be very easy to understand, and I'm going to do some exercise problem today. And units. In the past, not this class, I'm pretty sure this class everybody will do right, but usually in the past, the students screw up the units. If you screw up the unit, then answer is of course wrong. Solution is wrong. Then, for example, it affects the design, such like the thickness of the plate. And for this Taylor plate theory, it's very useful for not the final design, but preliminary design, things like that. And the application is mostly good for the valve design, penetration, or penetrator design. Any ship or underwater vehicle has a valve on the hull. When I say the valve on the hull, it's not a small valve. We are talking about 3,000 pounds, which is about 18 kilograms. The valve stick out from the hull. In the vibration situation, no problem. It doesn't affect much at all. But in the underwater shock situation, that valve has a mass. It has a tremendous acceleration, high G's. So mass times high G's, you have a tremendous forces, inertial forces, which can really fly out from the hull. When I say flew out, I'm not talking about just fly into the sky. No, in the water, they can just shoot right out. High G. So in my research lab, my students are working on the ship motion, ship acceleration to the underwater explosion. But when they look at it, when they look at their result, they're talking about the 1,000 G. Whoever handles the ship, they feel, oh, this 1,000 G, too high. And the patrol ship, small multi-hull ship, 3,000 G, oh, this is too much. In the shock situation, the acceleration is not too much. Look at that guy. So that's what the scary thing is. For example, for the valve, or you can say penetrator or penetration, because which takes seawater in and seawater out, and you have to have a proper well. Why? If you feel, oh, I feel this is feel that well, this shouldn't be good enough. No. For the shock, doing the shock testing, what I observed was it's just busted out. It welded by first level certified welder, but it looks very nice, you know, as you look at it. When it received a shock, it wasn't good enough, because right inside the well, when you take the x-rays and all that, well, it wasn't good enough. And in the shock situation, it wasn't enough. So usually lieutenant in Navy, they lieutenant or lieutenant commander, the rank in Army is like a major or a captain. They are working as a sous chef, superintendent in the shipyard, so they are really carefully examined. Otherwise, it's going to be dangerous after all. So here is what we're going to do. Pay attention on the units, okay? And this, when I say unit, I'm not just talking about the matrix or gravitational English unit. So when you do the conversion, you have to be very careful. I'm mixing matrix and English gravitational unit freely, so you can exercise all that. So here, charge of 120 pounds of HBS-1 is detonated underwater, 40 feet away from a steel target, constructed of 1 inch thick flat plate. Calculate the peak velocity near the center of the plate and the time that this maximum occurs. So, application of Taylor plate theory, and the first quantity you have to compute is M. What's the M? D. What's the M? Did you review the last Monday's lecture? Huh? You didn't? You reviewed? What's the M here? The area of that's a mass per unit area. The thickness is also taken care of. That's why we started. Why we started like that? Because it's an infinite size of the plate is infinite. So you have to deal with the mass per unit area. That's what it says. Then for the steel plate, usually 490 pounds per cubic feet. But that's, somebody could argue, wait a minute, I use 460 pounds per cubic feet, that's fine, depend on. But I just pick in this case 490 pounds per cubic feet, okay? But in metrics, what do you have for carbon steel? Do you have in mind some value? Really? Any values in mind in metric? I know this for the design. I work as a designer a few years at the beginning when after I graduate college, work as a designer. I feel kind of usually know in metrics that's what you're using it. Anybody knows, Jungwon? What's the mass density? Carbon steel, non-constructional steel. How about the 요건 I want you to find out yourself, stick it in your brain, or as a common sense for the mass density or weight density. Weight density make the matrix. Take a look at it.
7,000
7,000 cubic meter. To check it out, Suma is working in industry right now. So 7,800 kilogram per cubic meter. That's what it does. Check it out, you should know. So here, in the gravitational unit, roughly is 490 pounds per cubic feet. Okay, so I'm going to convert this guy into the cubic inch. Then 1 feet is 12 inch, right? So we replace the feet here as 12, right? Inch, which means we have to multiply 12 cube right here. So you have to divide by 12 cube. This is now this very elementary stuff I'm talking, but still very important. When you screw up, you end up getting the wrong solution, wrong thickness. So convert into the pound per cubic inch is 0.284. So that's what the weight density in pound and inch unit, 0.284, which is the weight of the just general carbon steel for 1 inch by 1 inch by 1 inch cube. That's what it is. Then mass is concerned that this is 0.284. Now I multiply 12 by 12 by 1, then divided by 32.2. What's a 32.2? That's a gravitational acceleration in, it's a g, which is a pound per. What's the unit of the g? In the feet per second square, right? So 32.2 is, in metrics is 9.81 meter per second square. So in gravitational unit it happens to be 32.2 feet per second square. So here is 0.284 is per inch by inch by inch. Then here I multiply, this is 1 inch, okay? So 12 by 12 by 12, convert back to feet again, because this is 12 cube, is feet cube. So this is now, everything's back to feet. If you do that, it's 1.27 pound per second square per cubic feet. Don't confuse the unit. The gravitational unit uses pound as a basic unit, but matrix is a kilogram. So, which is mass, here is weight. Okay? So, gravitational unit uses pound, like a feet, and second. Right? But for the matrix, it's kilogram, meter, and second. So that relation, just keep that in mind. So So that's sometimes confusing, but I don't want to see you making some dumb mistake. Unit-wise, this weight is the pound, and the metrics you use M, which is W over G. So here is a pound divided by G feet per second square. So you will end up having pound per second square feet. This is where this comes pound per second square per cubic feet here. But this case is just for, it's not the density. So for density unit, you have to divide it by per cubic feet. So conversion, you have to be kind of careful. And through the homework, I want you to do the sort of exercising by solving the homework. And the P max, what's the unit of the P max? This is all unit dependent. And the P max is pound per square inches. Don't feel, geez, why I'm using here in Asian country, I'm just using metrics, why I have to learn the gravitational unit. But now it's a global era, so you don't just stay in Singapore, you don't just stay in China or Korea, you move around anywhere in the world. So it's nice to know all different units, okay? This is unit dependent. This is like the K1. This is a W. This is R. R unit is feet. This unit is pound. And this is a charge type dependent constant. Remember 3.2? And it's all in unit dependent empirical equation. So it has 2070 psi, pound per inch square. And theta, what do you call the theta? Theta is decay constant, which shows the rate of the decay, right, of pressure curve. So this is, as I recall, is K2, and this is W. So K2 value for HBX1, as this is A2, and 125 pound feet. So this unit dependent, the theta is millisecond, 0.468 millisecond. So now this is all the ingredient is what you are computing. Then you can apply the equations for the result. And you can compute the beta. Careful on the units, okay? Final exam is kind of time checking. That time using a couple of one problems and checking the units whether you convert it properly. This is theta. The theta is millisecond, you compute it up there. But the units over here has to be unified unit. Like you decide. So I'm using, for example, pound and second and feet. Then you have to keep that. Every quantity you have to use the same units, similar unit. once you pick the basic unit as, of course, pound, feet, or inch, and second is you have to stick to that. So theta, I multiplied by 10 to the minus third. Why? Because the quantity I compute was a millisecond. So you have to divide it by 1,000. That's what this is in the picture. And rho, what's the rho? This is mass density, right? So mass density of the water. The sea water is 64 pounds per the cubic feet. So I divide by 32.2. Make sense? Which is feet per second squared. So 5,000 feet per second. So just to make sure that you use the right unit, then you're not going to screw it. The M we computed up there. So M we computed up there. 1.27 units is pound, second, and feet. Then you compute the, like that. Then you compute the T naught, then U max. So this problem set is very realistic problem. It's not just a mathematical problem. 125 pound HBX1. It's not big problem. 40 feet standard distance, very reasonable standard distance. And you have to compute that. I want you to go through the exercise at home. Y divided by, multiplied by 10 to the minus third. I want you to go through that. Y 144, 12 squared. And compute all this, and you have the U max is 36.84. What's the U max? Maximum velocity of plate. One is the plate. So 36. That unit feet per second, which is you divided by 3.2, which is about 12 meters per second, which is very reasonable. Get that here. Then you can estimate the average acceleration. You need to calculate acceleration quantity because to compute the inertial force. As you know, mass per unit area times acceleration. This acceleration is like the average acceleration. Why? Because this is U max at a particular time, right? And cavitation occurs right in front of the plate, then that's the maximum velocity you can achieve instantly for the duration of T naught, which occurs the maximum velocity. So you divide the U max by T naught, you can have not instantaneous the acceleration, but it's kind of average. That's good enough for, maybe good enough, pretty sure good enough for the initial design or preliminary design. To do the final design, final calculation, you might have to get into the finite element models, conduct the analysis, get the result out. But usually for the valve design, this approach is good enough to design the well model. All this is a word I want you to read. second example is much more realistic. This is a sea valve, or hull valve example. This is like a hull. Then this is a valve. Then you can take the water in or discharge the water out through the valve. This hull valve. Hull valve is about 1,650 pounds, which is approximately how many kilograms? About half. 1 pound is 2.2. 1 kilogram is 2.2 pounds. So if you divide by 2, it's about 800 kilograms. Your weight is how much? Your weight is about 50 kilograms. So I'm about 70 some kilograms. That's too high. But anyway, you get the feel. And the hull insole. This is a welder point right there. This is a welder point right there. You can have V-groove weld, all different kinds of the weld you can consider. The Korea shipbuilding, all shipbuilding companies, they have a faster welding skill in the wall. Do you know that? There's a faster welding skill in the wall. So now question is, this valve will receive a shock loading from 125 pound HPX1. The standard distance is about 20 feet. The diameter of the hull insole is about 30 inches. This is about 30-inch diameter here. This hull insole is about 30 inches. Determine the Umax, T-max, A average. You can compute the average acceleration, then you multiply it by whole thing, 590 plus 1650. Oh no, I'm sorry, this is a pound, right? You divide it by 32.2, right? Then you get the mass times acceleration, then you can get the inertial force, which is equivalent static loading. Then you can design for the weld moment. Okay? Then I used the killer plate theory to do the preliminary design of the weld and things like that. Remember, I applied the killer plate theory. Is it good or bad? Acceptable? You have to think about it. Because I am going to use the killer plate theory. What does it mean? What's the assumption? Assumption is thin plate and infinite plate, right? But this valve is not infinite. So there is the differences you have to really take a look at. Always look at assumptions, initial assumption. But for the preliminary design, that's good, perfect. Not the final design, but the initial design means I want to roughly know the weld size. I want to really roughly know whether this will survive in the shock situation or not. I want to really know this valve is part of the shipboard equipment. It's not the hull itself. Shipboard equipment is a valve. So for the damage, to assess the damage of shipboard equipment, what do you use? You're using shock factor. Yes or no? Yes. Then you apply the shock factor. then you have to take a look at whether this attack geometry, 125 pound HPX1 and 24 feet standard distance, what is the shock factor? You have to think a lot of different things, but I give you all the necessary ingredients. Then in reality, what you have to do, all the computation, you do yourself. Who judge? You judge yourself. And not clear, then what you're supposed to do. In Singapore, Willis, you give me a call. It's all you have to do. My students, mostly naval officers, like the captain, which is equivalent to colonel in army rank. He called me once from a long time of Iraqi war. They want to do something. They called me back, asked my concern whether they can make the artificial tsunami. I mentioned briefly to you before, whether I can make the artificial tsunami to wipe out the mines buried in the beach. My answer is no. You are not going to make the artificial tsunami, which is not a good idea, and it's not going to happen. So once we know each other, that's what you will do. Doesn't matter where you are. It's just a phone call away. One phone call away from each other. I called Orlando, I called Virginia the day before yesterday because they're supposed to send me the files to me, particular file, and he never sent it. So I called. Well, he said, "Where are you? You look like you're next to the door." I'm not next to the door, 10,000 miles away. But look like I'm calling him next to the door at 10 o'clock in the evening. 10 o'clock in the evening out there, and here is 11 o'clock a.m. So try to give you the motivations and all that. So apply the killer play theory. You have to know implication, assumption. A problem here, there, is once they got the equation set, empirical or analytical equation, they're just using it. That's the problem. So there is a DDAM approach, which is a dynamic design analysis method, which I'm going to teach you. So the shipboard equipment analysis. It was developed originally to do something like a 20 degrees of freedom model. One point in the model has how many degrees of freedom? Say 6. 6. 3 translational, 3 rotational degrees of freedom. And you look at any point in the structure. It can translate, it can rotate with respect to X, Y, and Z. Just like that. Right? So initially developed the theory for something like a 20 degrees of freedom system. Nowadays they are using for the multi-million degrees of freedom system. Is it good? So when the news shipbuilding company invited me out to give lectures, I said, this is wrong. This methodology is good for fuel, like 20 degrees of freedom system. Not, you're doing million degrees of freedom system, something like that. Has to be very clear. Then what else can we do? We have to look into assumptions and understand what's wrong for your approach. So here is using, I'm keep telling you, you have to review all the time the assumption behind it. And someone is working STX, someone is working STX, they involved in the shipbuilding. They are building the ship. One number, they can make a thickness as 3 times thicker than what they need. Then company lose money. So that's their responsibility, right? So they have to work, they have to know all the details. Anyway, so total weight of the valve. When I say valve, this is the whole thing, including the hull insert. Hull insert means is a base plate. Base plate, okay? When then it's going to weld here, when the shock hit it, this is the water side, this is wet insert, this is the water side, this is inside of the ship. Then the shock comes from outside, right, in the water. Shock comes in, then the whole part can just move and affected by the shock, underwater shock. So weight of the valve, that's what included this. When shock hit it, it's not gonna, it's all bolted here, it's all bolted. And this kind of works as one piece. So that's what you have to design the weld for. So when you add the two together, it's a 2,240 pounds. Then area of the hull insult, area is hull insult is 30 inch. Area D is 30 inch. So 30 inch the square, then you divide it by what? To get the feet square, 12 square. Inch is 1 over 12. It's 1 over 12 square feet. So you have to decide at the beginning whether you're going to use pound, inch, second, or pound, feet, second, or kilogram, meter per second. You have to decide yourself. In my position, I don't care in the classroom unless I say use metrics. Usually in the shipbuilding, you're using metrics, right? Yeah. So you have to use metrics in Korea, in Asian country, in Western, in US, maybe the only country uses gravitational. Then now, then you compute, I'm using here gravitational unit, so W pound divided by area per square foot, then you compute that. So this is the, right here is the approximation right there. So what I did was, okay, this is pound per square feet because I'm dealing with the area of the hull insert and assume the uniform thickness. That's a bad assumption, but that's what assumption of the kilogram theory. That's what you are using here. As a preliminary design, may be good enough. Then 456.2 pounds per 452.6, 490 is weight density, right? So 2C, this is square is not right. This is beneath that. This is only thickness. This is thick. So you're dealing with a 0.93 feet thick plate, which is multiplied 12 roughly 11 inch thick plate, which is not really desirable. But I said I use killer plate theory for initial design or preliminary design to really see what that would be. So that's what I applied the killer plate theory, and for the valve, this may be good enough, or this is good enough. You delete that square. Square here. And M, this is in time I divided by G, using the same, the 32.2, which is pound per square. Oh, this is 32.2, is feet per second square. Then I compute the M, which is weight, mass per unit area. And after that you compute the P max and theta, you all know that, that's easy. And the theta you have to compute, then T naught, with all the basic parameters you compute that, then you compute the U max, then you compute the average acceleration. So here is 992 G's. 990, about 1,000 G. That's a tremendous acceleration. That's what's happening. I don't have a specimen here. We conducted a lot of testing when I was in Naval postgraduate school. We go out, blow up, and you don't see here. In the future, next year, I have a provision to conduct the testing. So even if you're not taking this course next year, if I'm doing it, I will send you an email that you can really attend and see how it grow up. That's what I have a plan to do. So it's 992 G's. Tremendous. Then you multiply this guy to the mass of the valve. That's the force that you have to design your well. It's tremendous. So here equation using the killer plate theory are applicable only up to the time that the cavitation begins. Why is that? I compute the maximum, the velocity of the plate, right? U max at the point the local cavitation occurs. As local cavitation occurs, stops. Then P1 plus P2, remember? So beyond the zone, time zone, where the cavitation occurs, no longer true. So that you have to believe. The theory which I will introduce in chapter 5 tonight is almost all. I'll point out when I give a lecture, when cavitation occurs, it's a totally different phenomenon. Everything cut off, pressure cuts off. All the theory may not be applicable. Then the question is, what should I do in reality? What should I do? Cavitation occurs. But cavitation occurs, but it doesn't stay there for a long time. It quickly occurs, then surrounding waters will close the cavitation. Instantly disappear with the pulse of the shock pulse. then I can say as an approximation, just you can assume that there is no calculation. Okay, so you will be in the position to decide what to do. Doesn't have to be admiral or general to make such a decision. Usually, lieutenant in the Navy, which is captain on the rank, they decide what to do. That much responsibility there. And Hajan, section head, has authority to say what to do. Is what the summary is. Then example number 3, 125-pound charge of HPX-1 detonate at the standard distance of 25 feet, and the structure of 1-inch thick steel plate, then determine U mass, T naught, and plate momentum. What does it mean, plate momentum? And shock wave impulse. So in sophomore dynamics, you learn about the relation linear impulse is equal to change in momentum. You learn that? What's the impulse? Impulse is directly connected to the damage of the structure or the system. That you have to go. So, impulse. I did already. Impulse. Simply speaking, this is time t. This is like a force. Let's assume like that. Impulse is area under. Area is important. Area under. So impulse is Ft. dt is change in momentum. Mass. V2 minus, for example, V1. For the on-deck situation, initial velocity usually could be okay, 0. Or not 0. If you're dealing with the kickoff velocity, it's not 0. So that's what you have to deal with. So that's what you, I just say, compute the plate momentum and the shock wave impulse. Shock wave impulse is what the underwater explosion it could generate. The impulse is right trapped in the water. And some of it absorbed by the plate because it has a flexibility there. Do you see that? So that's why I put this in. And a few examples is good enough. If you solve all that problem, you're going through each line, then you shouldn't get any problem to do the homeworks, exam problems whatsoever. As you solve the military exam, I'm just checking whether you do it properly or not. And you all know this why. If shock wave pressure, you compute the shock wave and decay constant, and you compute the data, then T naught, then U max, then U max, you compute the mass times U max, which is really plate momentum per square foot, per unit. In this case, it's per square feet. because it's infinite play which we are talking about. Then this is equation for impulse. This is a 324.3. That's the impulse generated by the shock with a certain charge, weight, and standard distance. That much it generates, but it's only absorbed 77.5 by the plate. The other, this guy minus that guy, that much impulse is still left in the water. It could hit it later. So potentially only this much was used up, but still quite a bit are still there to reload to the system. Okay? Or it just could go away forever, I suppose. Now this is exercise problem I wanted to do. So whenever I assign, this due is next week. So today is Wednesday, due is next Wednesday. Okay. So you can really exercise the best idea, not giving you a hard time. So giving you a hard time, this is not the way. So I want you to sit down and do the exercise problem on Monday. Then tonight I'm going to start from here.